In this video, we're going to look at Coulomb's law and how it affects the attractions between protons and electrons between electrons and electrons in an atom. All the periodic trends depend on the arrangement of electrons in the atom as well as the electrostatic forces that occur between electrons and protons. The factor that determines the electrostatic force is called the Coulomb's law. Here's the equation where we have V representing the attraction or repulsion between particles, and it's measured in newtons. We have constant K with a value of 8.99 times 10 to the 9th. We have the charges of the particles involved. In Q1 and Q2, this would be for a two-particle system, and that's measured in coulombs. And then we have the distance, which we would measure in meters. This law basically makes two statements. The first statement is that the force of attraction or repulsion is directly related to the charges of the particles. If the charges of the particles increase, one or both, then the force of attraction or repulsion is going to increase as well. The other statement that this equation makes is the relationship between the force of attraction and the distance between the particles. As the distance between the particles increases, we see that the force is going to decrease, and this is an inverse relationship. Let's take a look at a couple of animations to help visualize this a little bit better. In this first animation you see, there are two equally charged particles, but with opposite charge. The arrows represent the attraction, and the length represents the strength of the attraction. As you can see, the closer the particles get, the stronger the attraction. This is what we would expect based on the equation for Coulomb's law. Distance is inversely related to the force. As the distance decreases, meaning the particles get closer together, the force is going to increase. In this next animation, we have a simulation of a nucleus with 4 protons surrounded by 4 electrons. Overall, the system is neutral since the number of particles with opposite charge is equal. Compared to the original simulation, there is also not as much attractive force between the individual electrons in the nucleus since the electrons are also repelling each other. If the number of protons in the nucleus is increased, the attractive forces increase equally among all of the electrons. In a similar simulation, we have 8 protons in the nucleus and 4 electrons surrounding it. If more electrons are added around the nucleus, the overall attraction to the nucleus decreases since there are repulsive forces between the electrons. Overall, the net attraction of all the electrons is still towards the nucleus, it's just that it's less because of the repulsive forces between electrons. But how does the attraction change when the number of protons and electrons increases at the same time? In this simulation, when the electron is added, the force of attraction decreases for the electrons. This is due to the repulsive forces of the electrons. But when a proton is added to make the atom neutral again, the overall attraction increases to a value slightly larger than the original. As this continues, you can see that there is a general increase in the attraction as more electrons are added around the nucleus at the same time the number of protons in the nucleus increases. This is due to the fact that the positive charge is concentrated in the nucleus, and the nucleus is treated as one particle with an overall charge equal to the number of protons. The charge of the electrons is spread out over a larger area, and therefore the electrons are treated as individual point charges. In the end, there's an overall increase for the electrons, even though we have added the same number of protons and the same number of electrons. The atom is still neutral, it's just the attraction is greater for the nucleus when you increase the number of protons.